Hey everyone. So we're going to walk through one more example using the Central Limit Theorem. And this one is about ACT scores. We know that the average ACT score is a 25 with a standard deviation of 3. We have many samples of 64 college students who took the ACT that were taking those samples of 64 college students. So we want to know what this mean of the sampling distribution of sample means is. So the mean of means is going to be equal to, as we talked about in the previous video, it's going to be equal to the population mean. So it's going to be equal to 25. The standard error, which is the standard deviation of the sample means, that is going to be equal to the population standard deviation, which is 3, divided by the square root of the sample size, in this case 64. So the standard error is going to be 0.375, which is much smaller than 3. So the data is not as spread out when we are using means as our data. If I find the mean of a whole bunch of values, we don't have as much spread because the mean is always going to tend towards the population mean of 25. So what shape is the sampling distribution? In this case, the shape is normally distributed because n is greater than 30. Now it doesn't say here that the ACT scores are normally distributed. I have a feeling that they probably are. But even if they aren't, because n is greater than 30, then the shape of the sampling distribution is going to be normally distributed. If we were only taking 20 college students for each sample, then I would not know the shape of the sampling distribution. So what's the probability that one student will score under a 30 on the ACTs? So we're looking for the probability that a single student gets below a 30 on the SATs. Okay. So 30 is my x value. My mean, my mean is going to be 25. My standard error, sorry, not my standard error, my standard deviation is going to be 3. It's just a single student. And so I'm going to use my norm.dist function like I have been. X value, mu, standard deviation, true. Since this is less than, it's a 95% chance. Okay, the probability that a student that I randomly pick gets under a 30, well, since the mean is 25 and the standard deviation is 3, 2 standard deviations above the mean is 31. So most of the data, 95% of the data, is going to be below that value. Now, what's the probability that 4 students will have a mean under 30? Okay, not that each student got under 30, but if I take the 4 students' scores and I average them, what's the probability that it will be under 30? Now, I already had a pretty high chance of just picking one student and getting a score that's under 30. Now I'm going to take 4 students and I'm going to average their score. And what that does is my mean is still 25, but now my standard error, because I have more than one person and I'm averaging their scores, I need to calculate the standard error. The standard error is going to be the standard deviation divided by the square root of 4, because I have 4 students. So that's going to be a 1.5 for the standard error. So norm.dist, I don't need a 1 minus because it's already less than x, comma, mu, comma, sigma, which in this case is the standard error instead of just standard deviation, true. Now I have a 99.9% chance that my 4 students will have a mean that's under 30. It's rare to find a single student that got above a 30 or a 30 and above. Never mind a student that got, never mind having 4 students that have a mean score that's over 30. That would be very rare. So we're going to do the same thing again. We want to find the probability that our score is less than 30, but now we're talking about 100 students. So I can pretty much copy and paste this information. The problem is now my standard error is going to be the population standard deviation divided by the square root of 100, and that's 0.3. So when I do norm, I can actually copy this formula and it should just work. Bam. I get 1. I have the norm.dist x comma mu comma standard error comma true, and I get a probability of 1. Now it's not exactly 1 because I'm sure if I did 1 minus the previous answer, oh no, it's giving me 0. It's 1. The probability is 1. I am certain that if I grab 100 students who took the ACT, that their average score would be below a 30. So why is our answer for part F the largest? Because I have more students in my sample, which makes it much more unlikely for the mean of that sample to deviate from the population mean. It's like the law of large numbers, okay? If I know that the mean is a 25, and I take one person and they got something above a 30, I'm not surprised. If I do 4 people, I'm a little bit more surprised. If I do 100 people, I can't even imagine that the mean of all of those people would be over 30. So now, give an example of an interval in which the situation part F would be the smallest. Okay, what if we did the probability of x being greater than, doesn't even have to be much bigger than the mean, but 26. If I find the probability that x is greater than 26, the sample mean, or the population mean, the true mean, is not in that interval. Any interval where the true mean is not contained within it would make part F the smallest. Because we would expect the true mean to be, or the mean of a sample of 100 people to be really close to the actual mean. So if we're finding the probability that we get above a 26, I'm not saying this is 0, but it's going to be smaller than the probability of finding one person that got above a 26, or 4 people whose mean got above a 26. So now we want to find a realistic range in which we would expect all the individual ACT scores to fall into. Again, we know the mean. We know the standard deviation of the population. This is an individual, so I'm just going to go 3 standard deviations to the right. So the mean is 25 minus 3 times the standard deviation is 3. That gives me 16. And I can copy this formula as long as I lock the reference to these cells. I can can copy this formula over and change the minus to a plus. So I would expect the scores to range from 16 to 34. That's a realistic range. For an individual, one person, if I randomly selected one person from the population, I'd expect their score to be somewhere between 16 and 34. Notice, the mean above 30, I'm barely getting an individual that is above 34. Never mind the mean of a group of people to be above 30. So just keep that in mind. It's that difference between the individual and the average of a group that I'm really concerned about in this scenario. All right, well, that's it for the central limit theorem. You can find your problem set in the course content section of Blackboard.